Okay, well, we are ready to wrap up Chapter 7 with a section on fluid pressure and fluid force. Okay, so let's define a couple of terms first. Fluid pressure. Fluid pressure is defined this way. P is equal to W H, where W is the weight density of a fluid, and this is a number that's unique for any particular type of fluid. Of course, the one we're going to use most often is water. The weight density of water, 62.4 pounds per square inch. I'm sorry. .4 pounds per cubic foot. Okay, and then H is the height of fluid above an object. Okay, since we're using, pounds per square foot, we should use feet for this to keep our units the same. Okay, working these problems, we're going to use something called Pascal's principle. Okay, and Pascal's principle tells us that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. Okay, and we could say that pressure is given in units of force per area. Got a big A. And so if I want fluid force, I just manipulate this equation a little bit. I get force is equal to PA. Okay, let's look at an example. In our first example, we've got a tank of water here, and there's a flat rectangular plate submerged 6 feet into the tank of water. And we want to find the force on that submerged sheet. So again, we've got P is equal to our 62.4, our density, times 6 feet, since there's 6 feet of water above the plate. And when I multiply this out, I get 374.4 pounds per square foot. Okay, now we're going to look at the area of this plate. Rectangular plate, it is 3 feet by 4 feet. Okay, so I'm going to multiply these two numbers together. 374.4 times 12 gives me 4,492.8 pounds. Okay, so this is basically the weight of the water on top of that plate. Okay, and I would get this result whether I had this plate in a tank, or in a swimming pool, or in a lake, or in the ocean. Well, not the ocean because it's salt water. But any body of water, the size of the body of water does not matter. It's just the size of the plate that matters. Okay, you might have noticed in that problem that we didn't use any calculus to find our answer. That was basically some simple arithmetic. And that was because the plate was flat, horizontal in the water, and so the pressure was the same everywhere on the plate. But what if we wanted to find pressure on a vertical plate? Now we've got more pressure on the bottom of the plate than there is on the top. So now we're going to have to use some calculus. Okay, so let's say this is our vertical plate. And here's maybe a little representative sample of that plate. And we'll call this width delta y. And the distance of that little rectangle is h of y, which is equal to negative y. This is assuming that we consider the surface of the water to be 0. And then the length of this plate we'll call L of y1. Okay, so we have this integral now. Integral from C to D. W times h of y times L of y dy. Okay, once again, h is the depth of the fluid, and L of y is the length of the plate at that depth. Okay, let's work a problem. We're going to look at a water gate that might be in a dam or some other similar structure. But this water gate is in the shape of a trapezoid. Okay, and I'm only putting points on this side because this is an isosceles trapezoid. So it does have symmetry down the middle. And we're going to call this distance x. And of course, if I have a representative rectangle down here, this would be my h of y, which would be equal to negative y. Okay, and once again, I'm going to put my x-axis at the surface. Okay, so this point is 4 feet below the surface. This point is 9 feet below the surface. Okay, now it would be possible I could put my x-axis right there at the top of the door, and I would get a different answer. But it's well, we'll get the same answer. I could put my x-axis right at the top of the door, which would change my calculation some, but I would get the same answer. So for right now, I'm just going to leave that up at the surface of the water. Okay, the first thing I need to do, I need to find the equation of this line. So using my point slope form, I have y minus negative 9 is equal to m times x minus 3. Now I have to figure out m. So up here I'm going to have negative 9 minus negative 4 divided by 3 minus 4. So negative and negative makes plus. I get negative 5 over negative 1, so just positive 5. So putting that back in this equation, I have y plus 9 equals 5 times x minus 3. I'm going to move the 9 over here and multiply out. So now I'm going to have 5x. I had negative 15, subtracted another 9, so minus 24. So my equation is y equals 5x minus 24. Okay, let's get rid of all that calculation. Okay, we are talking about water here, so my W is going to be the 62.4. And I'm going to integrate from negative 9 to negative 4. And my height is going to be negative y. And my length is going to be we're going to take that y equals 5x minus 24 and solve for x. So now I have y plus 24 divided by 5 equals x. So let's write that over here. X equals y plus 24 divided by 5. Okay, now looking at my picture, I see that x is only from the middle out, so the actual length of my representative rectangle is 2x. So 2x is going to be 2 times y plus 24 over 5. Now let's put in here. Okay, let's work a problem that's going to require a little integration. In this problem, we're going to have a water door. This might be in a structure like a dam. And I'm going to set it up so that the x-axis is at the surface of the water, and this door begins 4 feet underwater, so that point is -4, or 4, -4, and this point is 3, -9. Okay, I have the y-axis run right down through the middle of the door because this side and this side are the same. So if I find the force on one side, then I can just double it. So this distance from the middle to the edge is x. Here's my representative rectangle with the width of delta y, and the depth of it is h of y, which is equal to -y. Okay, let's use our integration and then the length of this rectangle is going to be L of y. To find this length, I need to know the equation of this line so I can find x. So we'll use the point slope form. Y minus -9 is equal to m times x minus 3. Now I need to find the slope. M is going to be equal to -9 minus -4 over 3 minus 4, so I end up with -5 over -1, so the slope is 5. So now I have y minus -9 is equal to 5 times x minus 3. I want to solve this equation for x to get that expression. So now I have y plus 9 equals 5x minus 15. So I add 15 to both sides. Y plus 24 over 5 equals x. Now the actual length of this rectangle is 2x. So I have to multiply this by 2. Okay, so this is our expression for x, or for 2x. 2x is equal to 2/5 of y plus 24. Okay, now we'll use our equation for force is equal to the integral. We'll put the w out here since that's a constant. We're going from -9 to -4. And our h of y is -y. And our L of y that we worked out is the 2/5 times y plus 24 dy. Okay, I'm going to go ahead and take out the -1 and the 2/5. I'm going to change the w to 62.4 since we're working with water. 62.4 negative times 2/5 times the integral from -9 to -4 y times y plus 24 dy. Okay, 2/5 of 62.4 Okay, now I'm ready to multiply and integrate. We've got negative 62.4 times 2/5. This would be y squared, so that would be y cubed over 3 when I integrate. 24 is going to give me 12y squared. And we're evaluating from -9 to -4. So I'll work all that out. I have negative 62.4 times 2/5 times negative 1675 divided by 3. Crunch all the numbers and get 13,936 pounds. And that's the force against that door. In the last problem, we set up our coordinate plane so that the x-axis was on the surface of the water. This does not always have to be. In this problem, we're going to set up the axes a little bit differently and work another problem. So right now this is a viewing window for perhaps an aquarium, and we see that the window is 8 feet under the surface of the water to the center of the window. And this time we're going to set up the axes so that the window is at the origin. Okay, and it has a radius of 1, and this distance here is 8 minus y. Instead of just negative y, it's 8 minus y. Okay, so in this problem we're also again going to take advantage of the symmetry, not only side to side, but we also have symmetry top and bottom. Okay, so let's take a look at this. As I said, our depth h of y is the 8 minus y. Okay, here's our representative rectangle. Again, the height is delta y. And the length of the rectangle would be 2x. Okay, now we're going to use the equation for a circle there. X squared plus y squared equals 1. And solve that for x. Get x equals the square root of 1 minus y squared. But again, x is only half of that rectangle, so this is going to be 2 and 2. And that'll be our Ly. Okay. This problem, they tell us that we're actually working with seawater rather than fresh water. So our weight density is going to be 64. So let's set up our integral. And we're going from negative 1 to 1. So there's my L of y. So let's set up our integral now. Start with 64, and we're integrating from negative 1 to positive 1. And then our h of y was 8 minus y. And L of y is going to be 2 times the square root of 1 minus y squared dy. Okay, we're going to separate this into two integrals. In the first one, we're going to multiply the 2 times 8, of course, is 16. So we're going to have 64 times the integral from -1 to 1 of 16 times 1 minus y squared, square root of that. Minus 64 times 2, that's the 2y there. We just took the 2 out. Y minus y times square root of 1 minus y squared dy. Okay, this kind of looks like a lot, but it comes out simpler than you think. In the second integral, we have an odd function, and we're going from -1 to +1. So since the integral is odd, integrand is odd, this is going to be 0. So that means all we really have to worry about is this part. Okay, so we're going to take some different things out here. The 64 is already out. We're going to take out the 16. Okay, and then we know that this is the area of a semicircle with a radius of 1. And so geometrically, we can just replace this with pi over 2, which gives us a total of 512 pi, which is approximately 1,608.5 pounds. Okay, so here's an example again. When I set up my axes to be right in the center of my shape, and instead of having the x-axis be at the surface. Okay, this is the end of chapter 7, and I'll have your test posted for you soon.